Thank you for inviting me to this nice workshop. I enjoyed the last one. I think it was, yeah, I forgot where it was. But yeah,
2018 Madrid, yes.
I did enjoy it. So, yeah, the title is, yeah, a bit off maybe to what I present, but still close enough. So let's start with introduction, motivation. So why human-robot collaboration? Because at the moment we don't have robot intelligence that would be equal to the human. So we still want to use the human cognitive capabilities to combine them with the robot superior speed, precision, and payload capacity. So we want to combine the advantages of both. And in any kind of co-manipulation or interaction scenario, it's crucial that you can control the impedance of the robotic arm, and even human, as we will see, to account for unstructured and unpredictable environments. So when stiffness control is beneficial? So I think I put this slide here because I think even among ourselves, maybe we don't completely agree, but I see three main points where you need to control the stiffness. So for example, first is safety. So if you are in an unknown environment, let's say someone closes the light and you're in the dark, then you probably want to lower your stiffness in case you hit something, that you don't damage your arm or damage the unknown environment that's out there. This is a case when you have to decrease the stiffness. And then it's precision and robustness. In this case, is the opposite. So when you have some unpredictable environment that's kind of perturbing you and you want to control the position precisely, let's say I'm trying to drill and something is moving, let's say my base of the robot is moving, then I need to increase the stiffness of the arm to counteract these perturbations. And last, which is not relevant for most of the robots that most of us use, except maybe for Tom, it's actually to improve the energy efficiency. To kind of, this requires a mechanical impedance, actually, not just controlled virtual impedance, so that you can store the energy in the spring of the actuator and then release it. So you have to have correctly timed change of the stiffness. So let's see for the collaborative robotic case. So here I have this sawing example. So in order to properly corroborate and pace each other's actions and not oppose each other. So when one agent is pulling, let's say if the robot is pulling, the human should become soft in order not to oppose the robot. And when the saw reaches the robot end, the humans should start pulling. And this is done by exchanging the stiffness. So one agent has high stiffness, the other low, and then they would change based on the task state. And of course, in this case, we also use force controller, so hybrid force impedance controller. Not always is enough to have impedance controller. So force controllers are very useful when you want to control some stable contact with the environment. So we can combine the two. And not, yeah, Sylvain already mentioned it, but impedance is not just controlled actively by actuators, but it's also determined by the configuration of the robotic arm or any kind of structure. And this we can get through the manipulability measure. So we have here force is the red, force manipulability is the red, and velocity is blue. And they are orthogonal to each other. So in this configuration, you can sustain huge forces in this direction because you're almost in single configuration. So your structure of the arm actually supports a lot of force. But at the same time, you cannot move much in this direction because you're almost in singularity. But on the perpendicular direction, you can have small movement in the joints will produce large movements at the end point in this direction, but not in this direction, as you can see. If you're in singular, when you start moving your joint in this instantaneous configuration, it's not going to even move in this direction. And this is, yeah, basic mechanics. So we want to also exploit this. So I'll just show you this video of the sawing. Maybe you saw it a few times already. So here you have to exchange the impedance in order to to facilitate nice collaboration. And also, yeah, we exploit this manipulability ellipsoids. So if the human changes the configuration of the arm, the robot tries to optimize for the manipulability, because you want to keep sawing in the direction that you can pull the most of the forces. So, but also then environment stiffness is important. So if the environment gives you a nice constraint, then you can exploit this constraint. Here, we are not even controlling the stiffness in the translational axis. It's completely compliant, so it lets the robot move it around. And then it's the environmental constraint that keeps the tool in sight. And then we just used joint torque, so we just increase the stiffness rotationally. So ergonomics is also important, especially human ergonomics in such co-manipulation scenarios. So this is a nice graph from Nevis Hogan, a really nice paper. If you haven't read it, go read it. So if human is doing the stiffness, high stiffness, actually that's very costly. So it will cost you a lot of energy. So we actually want to avoid active control of impedance or high impedance when it's not necessary. So that's another reason. For example, here you can have the equilibrium angle of your joint at the same place, but with the different muscle activations. Since the co-activation is the same, the position will not change. But you can see with these two huge muscle activations, you will get a lot of energy that you will spend. And yeah, that's why we want to actually exploit the configuration rather than the active stiffness behavior. So this framework now optimizes the configuration of the human arm to optimize for manipulability. Here is another one. It's just like a handover task. So now I'll go quickly through the TELE-IMPEDANCE, which is a teleoperation that allows impedance commands. I'll first show one interesting video. So here we are kind of teaching the human robot to counteract force perturbations on the body. So the human is operating the robot by its own body, and then it also gets the feedback at the center of mass, like the forces that robotics experience at its own center of mass. So we are mostly learning the admittance because we check the forces and then we have motion as a reaction. But in the end, mechanical structure doesn't care whether you call it admittance or impedance, because in the end, you have to produce forces to get the motion, and if you move, you also produce the forces. So it's mechanically, it's the same thing. This one I'll skip. So now I'll go into TELE-IMPEDANCE concept. So this is a teleoperation where you have commanded motion with an interface, but you also have additional interface that you can change and command the impedance of the remote robot. So here it's a very simplistic interface that we developed. So it's kind of like a push button. The more you push, the more stiffer the robot becomes. And in this case, we use, again, we like to saw. So we use TELE-IMPEDANCE to actually teach the robot how to collaboratively saw with another human. So we used motion command interface, which is optical motion capture system, and we used muscle activity measurements to measure the human muscle activity and then transfer it to the robot stiffness. Of course, this is a different times. EMG can give you more information, but it's also more complicated to equip and so on. And in the previous case, and also in the original TELE-IMPEDANCE setup that was proposed by Arash Ajudani, there was no force feedback. So we want to introduce also force feedback so that the human can actually also feel what kind of stiffness it's actually being commanded. But then we have here an example when you also have a proper haptic device that can give you force feedback. So in this case, the human is teaching the robot. So first, now it commands low impedance so that this bolt fits nicely into the groove, and it also stays compliant inside. This is very important for the next slide. And when you go outside, you can increase the impedance because it's just moving on the air, and you can be counteracting perturbation nicely if someone is bumping into the robot or whatever. And then when this is learned through the teleoperation, the robot can reproduce this at different speeds. So this is slow speed, higher speed. And you will see now why it's important to be compliant when you are inside. So the environmental constraint already provides the stabilization for your robot. So, but you should be compliant inside, because if there's some perturbation or some interaction with the human unpredictably, you could break the robot equipment or even injure the human if you are stiff inside. So yeah, this might be a nice discussion at the end with Donghae and Sylvain. So they typically propose that when you have repetitive positional trajectories or demonstrations, you would imply that the robot should be very precise there and very stiff. But in this case, this would actually not work because environment gives you stabilization. You would be very repetitive inside the groove of that part. And of course, if you apply this variance-based method, it would actually give you very stiff behavior inside this part, and this is very dangerous. But from the human demonstration, you can use the human cognitive capabilities, and it can then command or teach the robot the inverse strategy of that, which sounds more reasonable at least for this task. And also for many interaction tasks, I would argue. So then we have, in TELE-IMPEDANCE, we have different command interfaces for the stiffness. So we can have electromyography that measure muscle activity, or we can have grip sensor, force grip, and then we can have like some external devices that are not coupled with the human neuromechanical system. So if you have interfaces that are coupled with human neuromechanical system like EMG, electromyography, that measure muscle activity, then if you get some feedback, this force feedback will actually act as a perturbation to your position, and you will naturally, your reflex will naturally also stiffen up your muscle. But if you want to command actually low impedance, because the task requires so, then this reflex based on the force feedback will actually unintentionally increase your stiffness, the commanded stiffness to the robot, and this will corrupt your task. So the commanded impedance is actually tendon impedance plus the reflexive change that comes from the force feedback. We did some human subject experiment. So we tested it on this interface with one interface and the other. So human was doing some task, and then suddenly something perturbed it, and then we measured how the commanded impedance unintendedly changed. And here it's with this external interface, which is completely decoupled or almost completely decoupled from the neural mechanical system of the human. And of course, each one has some drawbacks and some advantages. So for the coupled interfaces like EMG, it's more intuitive there, because sometimes it can even help you. So if you want to actually counteract that positional perturbation, you will actually naturally stiffen up your arm, and that will help you. But the human doesn't have the complete control over command impedance. In the decoupled interfaces, it's a bit less intuitive, because when some sudden perturbation comes, you have to stiffen up intentionally, like cognitively. But in the end, if you have to control low impedance constantly, this will not corrupt that task. Yeah, that's pretty much it, because I ran out of time. And these are some of the colleagues